fired combustion processes with catalytic flue gas analysis. Now, for today's webinar, we're going to talk about the nuances of high hydrogen fuels and how catalytic flue gas analysis can optimize these combustion processes by being able to detect both hydrocarbons as well as hydrogen at different concentrations. So for today's agenda, we will be covering just some of the trends associated with decarbonization and driving the use for hydrogen in fuels today. I will also talk about optimized combustion, what it is, some of the inherent challenges when it comes to safety and efficiency, and how do you look at that balancing act of making sure that things are optimized but also safe. So we'll look at that. We'll also talk about the 3 critical rules of flue gas analysis, and especially when it comes to high hydrogen fuels, what to think about, how does the flue gas analyzer play a role in that. We'll also talk about the combustion properties of hydrogen, some of the physical properties of hydrogen, the risks that are inherent to those nuances on the physical and combustion properties, and how they compare to methane, and what we have to think about as a result. We'll also talk about catalytic detectors, how catalytic detectors can be leveraged in flue gas analysis to monitor for hydrogen and detect unsafe conditions. So as mentioned, feel free to put any questions in the chat, and if I can fit it in, I can fit it in. Otherwise, we can talk about it at the end of the session. So just to get us started, let's talk about some of the trends in decarbonization that we're seeing today. One of the biggest things to start off with is just the movement towards decarbonization is a global issue that's rising across governments and corporations. Many governments globally have evaluated the role in climate change and seeing the need to reduce greenhouse emissions, including carbon dioxide. And that being said, there's still many industries that will require combustion for power and for heat. Some of these include some of the hard to decarbonize industries like steel, cement, and chemical industry for very high temperatures, and then in some cases, different limitations associated with mobility in vehicles, so ships and air traffic and trucks as well that carry heavy loads that are going to continue to require combustion for power and for heat. Now, this is important to think about because combustion is still going to remain even as the world decarbonizes. And one thing to think about is that there are many different ways to reduce carbon dioxide emissions. And those include carbon capture to remove the carbon emissions from the combustion process directly or indirectly in the fuel. Also through electrification, and that has a place as well in some of the decarbonization effort. But when it comes to really combustion, some processes just require high temperatures and require high demands on power and heat. And that's where hydrogen fuels can generate heat without the carbon dioxide emissions. So it is important to realize that combustion processes will remain important in our future and as we move towards the energy transition and decarbonization. Now, just to look at these 3 different methods again in just a little closer detail. So let's think about combustion. Let's talk about navigating these pathways of decarbonizing combustion. If we start with carbon capture, again, carbon capture can remove the carbon dioxide directly from the combustion process. It could be before the burner or after the burner. And it's helpful if you have a very centralized emission source where there's one big process that's generating a whole bunch of CO2 and that can capture it. Maybe it's one big fired heater. In that case, it's more economical when there's a really centralized pipe or duct that can contain all of these emission sources. The challenge is when you think about a typical refinery or chemical plant where you have many small dispersed sources of combustion, maybe for a fired heater, maybe for a reformer, maybe for a boiler, and all these dispersed sources of carbon dioxide emissions can make it difficult to connect them in order to pull them all together to actually use carbon capture for what it is. So it can certainly require a significant amount of equipment, of ducting, of extra time and energy to pull these emissions together. Now, carbon capture is one way to decarbonize, and we talked about that. The next way would be electrification, like we talked about as well. That's very well suited for new plants, for greenfield plants where they have the opportunity to use lower temperature heaters with electrification. It still requires some amount of power source, but if it's low enough a temperature application, you could have a electric fired heater. Those are certain things in discussion, certainly today. But again, the challenge is how do you retrofit the brownfield? How do you retrofit existing plants? And how do you have a reliable power source? I've heard of even some refineries using coal-fired power still for the reliability of their boilers. I've also know that there's a lot of natural gas-fired boilers for that have a natural gas for the steady stream of power sources. So something to think about, especially when it comes to electrification. There is a place, just can be much more of a difficult consideration when it comes to the existing plants and existing facilities. Then it comes down to hydrogen. Let's evaluate hydrogen as a fuel as well. So hydrogen certainly depends on how the hydrogen is generated. That we don't want to be agnostic to where the hydrogen comes from. But if you were to put it into a burner, it's still going to burn without carbon dioxide emissions, just by the sheer nature of just being the hydrogen molecule. The advantage here is that you can keep your fired heaters, you can keep your boilers, you can keep your different fired equipment that has many point sources, many small dispersed sources. So if it can be used for both the centralized sources that are easy to maybe have one big duct for all the CO2 emissions, it can also be used though in those ones as well as for the many small dispersed sources, so that the transition from a natural gas to a high hydrogen fuel or hydrogen fuel can make it a much more straightforward transition. There's also just the reduction of footprint. It's important to think about, especially within existing facilities, that there's not always enough space to just add another piece of equipment for carbon capture or for electrification, and so minimal footprint is minimal impact on footprint, and a minimal impact on even the carbon source as well. Not having to think about changing the burner, doing the necessary things to handle hydrogen, but also not egregious where it's a lot of extra time and energy and effort to make the change. So it has a much less impact compared to some of the other methods presented. Also, like I mentioned, zero plot space requirements near the combustion location. So a lot less. If you have an existing heater, if you have an existing boiler, it could be put right into the same place without having any extra major pieces of equipment or ducting to support the reduction of CO2 emissions. And then finally, hydrogen fuels is not a new thing. There's a lot of industries, especially in the refinery sector, where they generate a lot of hydrogen as a byproduct, and that's used as refinery fuel gas. And this is something that we've seen for decades that can be safely detected in flue gas and also used to optimize the combustion process. So if we look at it together, we can really see that hydrogen as a fuel offers the versatility, especially for existing combustion processes. Okay, so that's really what's the prompt here, and that's really what's caused us to think about how do we handle, like, what's driving high hydrogen fuels. If we look next into optimized combustion, I mentioned that a couple times, but how do you optimize combustion? What does it even mean, and what is the safety efficiency challenge that we're confronted with as we optimize any combustion process? Well, the first thing to think about, I don't want to go too much into the basics, but I think it's important to recognize that in order to generate a flame, any combustion process requires oxygen, fuel, and heat. And that's going to be important for any type of flame. You're going to need some type of oxygen, you're going to need some type of fuel, and some type of heat source. And the thing is in any combustion process, there's also going to be some amount of incomplete combustion. There's going to be some amount of combustibles that we call it, or intermediate products of incomplete combustion that we call combustibles. And in this case, we we recognize it as carbon monoxide and hydrogen. But products of incomplete combustion that are really created from the nature of reality. There's always going to be some amount of poor mixing. You can't have perfect mixing. There's always going to be some amount of changing in the fuel load. There's always going to be some potential malfunction of the burner that you have to consider, whether it's fouling or an issue with the burner tips. And then also with variable fuels and changing fuels. And as you change fuels, you can also, when you switch from one to the other, you have the potential of creating more combustibles. So in all of these cases, it's important to think about the possibility of there being some amount of incomplete combustion. And then as we think about relevant combustion measurements, I'll get to this towards the end as well, but as we think about relevant combustion emissions and measurements, I'm going to go into each of these next, but it really comes down to needing some amount of excess oxygen measurement to make sure that you have enough oxygen on the outlet, make sure that you have that as a set point. Also, it's important to measure some amount of combustibles because that can help with safety. We'll get into that. We'll also talk about optimization and how combustibles play into that. It's also helpful to detect some amount of hydrocarbons or methane if you were to have a flame out, or even if you have a high hydrogen fuel, percent levels of hydrogen. And then finally, when it comes to a flue gas analyzer, it's important to make sure that you have a representative sample, that measurement, that there's enough flow in the analyzer that is making sure that there's an accurate representation of the process. So we'll get into many of these in this presentation, but I just want to give a quick overview because these themes play out and it really comes down to the basics of combustion and what's going to be required for that flame. So when it comes to any type of fired equipment, the perfect state would be what we call stoichiometric combustion, where you have the perfect amount of air with the perfect amount of fuel with the maximum heat transfer, driving complete oxidation to complete combustion to carbon dioxide and water, maximum efficiency. Again, this is the perfect scenario. In reality, this is not exactly achievable. And in reality, we have to operate with slightly excess of air at the burner. And as we operate slightly excess of air at the burner, we have a slight excess of oxygen at the stack or downstream. And just like you can see here, there's a slight excess of oxygen at the burner, and that drives an excess of oxygen in the flue gas. Now, in these cases, regardless of the application, we see some amount of low combustibles. And we recognize it and measure it as combustibles as the combination of carbon monoxide and hydrogen. But either way, there's going to be some amount of ppm levels of combustibles that we're going to see, as well as some ppm levels of NOx. And so while in this specific case, we're operating with a slight excess of air, in this case, 20% excess air, it's a little bit less efficient, but is also safe. So you still have a useful heat transfer, and it's also safe compared to the prior case. Now, the risk that we're concerned about is what happens when you don't have enough oxygen. What happens when you don't have enough air at the burner? If you have an excess of fuel because of a burner leak or of a flame out or some type of unsafe condition when you're switching fuels, that excess of fuel not only is less efficient, 35% less efficient, but also generates a very unsafe condition of percent levels of carbon monoxide, of hydrogen, of incomplete combustion. There are certainly cases in industry where you need partial oxidation, like partial oxidation or even autothermal reforming. But when it comes to a standard thermal oxidizer, fired heater, boiler, kiln, in any of those cases, you don't want to see extremely high levels of combustibles. That presents an unsafe condition with the potential for even more consequences. So this is something that we want to detect and monitor for. And one thing I want to highlight is that there is no excess of oxygen in this case. So this is substoichiometric. This is below the perfect mixture of air to fuel. So that's one thing to highlight there. There's no excess oxygen in this case either. Now, one thing I want to point out is if you were to plot the correlation between the excess air at the burner and the excess oxygen in the flue gas, you could actually calculate this for any hydrocarbon, and you can also calculate this for hydrogen. But if you were to take, say, about 3% excess oxygen, maybe a little bit higher than that, 3% excess oxygen, you'll see that correlates roughly to 20% excess air at the burner. Okay, so about 3.2% roughly correlates to about 20% excess air at the burner. What that means is that the burner has a safety margin of about 20% excess air at the burner. So you have this inherent safety margin built in. Now, if you were to take 2%, again, 2% excess air correlates roughly to 12% excess air at the burner. So the correlation of 2% oxygen in the flue gas is around 12% excess air at the burner. And that's important to know because you've reduced your safety margin at the burner, but you've also made it a little bit more efficient. So there's some trade-offs there, and we'll get into those. But one thing to think about is if the typical range is between 2 and 3% excess oxygen in the flue gas as a typical range, then that correlates roughly to 12, 11% excess air at the burner. Now, if you were to repeat this calculation for other hydrocarbons, it's actually very similar trend. So the lines actually are very strong when it comes to the correlation between excess oxygen in the flue gas versus the burner. I did recalculate for hydrogen, and with hydrogen you get a slight increase, so you get about 12%. 2% would roughly correlate to about 12%, and 3% would roughly correlate to about 22%. So very similar, not much of a difference as you can see. So in either case, when it comes down to excess oxygen, if you have about 20% excess air at the burner, you're going to have about 3% excess. You should expect to see about 3% excess oxygen in the flue gas. So the correlation holds pretty strong. And this is important because in many cases, the oxygen measurement from the stack can drive the combustion air to the burners, and it provides a secondary measurement to verify the air to fuel ratio at the burner. And like the same with thermal oxidizers, excess of oxygen in the downstream of the firebox, that correlates directly to the secondary air and whether or not they need additional air to fully oxidize the contaminants in the waste gas. So in either case, the excess oxygen provides that visibility into the air to fuel ratio at the burner. So we're going to build out these critical rules of flue gas analysis as we talk about combustion optimization. But for the first rule of operational set point, based on an excess of oxygen in the flue gas after all combustible compounds are consumed, it does correlate directly with the air to fuel ratio at the burner. It is also ensures that there's enough air at the burner, again, for a safety margin. Now, that being said, the rule of optimization is the next thing we can talk about, and this is really where we have to first set the stage with operational set point before we can talk about optimization. So if 2% is a typical operating set point, that also represents some amount of CO2 emissions, some amount of NOx emissions as well. And as you increase your excess oxygen for greater safety margin at the burner, you also have a higher excess oxygen, which has a higher CO2 correlation and a higher NOx correlation because you're using more fuel to burn the inerts. And then at 4%, it's even higher. So as it increases, yeah, there's extra safety at the burner. There's also a higher emission in fuel consumption as you increase as well. So that can really be generalized as higher CO2 emissions, higher NOx emissions, higher fuel usage as well. Now, when it comes to combustibles measurement is very different than in excess oxygen measurement. For excess oxygen, it increased. Well, combustibles, as you have more excess of oxygen in the flue gas, you have more oxygen available to fully oxidize the carbon monoxide and hydrogen, the combustibles. And so as you increase, you have lower and lower levels of combustibles. I will say that the risk is as you go lower and lower with excess oxygen, you have higher levels of combustibles and the potential for breakthrough. At this little point of inflection, or this little turning point, it goes from linear to near exponential increase. And so we can't just go to stoichiometric conditions. We can't just go to 0% oxygen. As we go to 0% oxygen, there's not enough good mixing. There's not enough contact between the fuel and the oxygen in the air for a good combustion process, for a good combustion reaction. As a result, as you get lower to stoichiometric conditions, you also have astronomically higher combustible levels. And so the opportunity to optimize combustion is when you put these two measurements together. So what may be 2% as your typical operating set point could potentially be reduced to 1% or slightly above a 1% as a more optimum control point that is still away from combustibles breakthrough, but still less than the original set point to reduce your fuel levels. And so again, the excess oxygen provides that operating set point. You need it so that you understand that you have complete combustion, full combustion with enough oxygen in the flue, enough oxygen in the flue gas. But you also want to make sure that you have combustible monitoring, so that if you were to look to optimize your combustion process, lower the excess fuel levels, you could, with visibility on not being too close to combustibles breakthrough, but also to be in a safe range as well. And so lower excess oxygen levels obviously reduce the emissions for CO2 emissions, reduce fuel consumption, and also avoids the potential risk of combustible breakthrough. Now, that's just an overview of optimized combustion. And again, this is for illustrative purposes. And the reason for that is because the target combustibles level really depends on the fuel that you're using. Natural gas in the burner design and the firebox design might be suited for lower levels. So you might be able to go lower than 1% in some cases with natural gas. But as you go with oil requires a different atomizing, more additional time, more additional oxygen available to fully combust oils. Coal is even more so. So there's really no set recommendation when it comes to what's the target percent excess oxygen. It's really by process basis. And if we were to investigate further, well, what are the varying factors? Well, fuel's different, coal versus oil versus gas, but also mixing dynamics of the burners, humidity changes. High humidity climates can be more susceptible to requiring more air, obviously more fuel because of being able to overcome the humidity in the actual combustion air. There's also the fouling of the burner. There's also mechanical wear, changing loads. There's really no fixed value because you want to make sure to give enough safety margin if you were to switch fuels that you could do that in a safe way. So for all these reasons, there's no fixed value for what's the optimal set point. As a result, we recommend measuring combustibles as a means to drive for safety and also for optimization. So going back to the three critical rules of flue gas analysis, the rule of optimization really allows you to monitor for the health of the combustion process. How much incomplete combustion do you have in the form of carbon monoxide and hydrogen? What is the secondary reference point that you have so that you could optimize the excess air at the burner? And then also, how can you leverage these measurements together, oxygen and combustibles together, to really reduce the CO2 emissions, reduce the NOx emissions, and ultimately reduce fuel consumption? Now, the next thing to think about is safety, and we've talked about that a little bit already. We talked about safety when it comes to monitoring for combustibles breakthrough. It's very important that we monitor for ppm levels of combustibles so that we can alert for some amount of incomplete combustion. Now, that's for ppm levels, but what about percent levels? We do have a methane detector that can measure light hydrocarbons. And what we've found is that if there's some type of leaking fuel at the burner or some type of loss of flame for whatever reason, we have had indications during normal operation, in addition to the light off, but during normal operation, where you can detect the loss of flame because that, even though it's above the ignition temperature in the firebox, there's not enough good mixing, there's not enough time for the hydrocarbons to fully oxidize and fully react. So you will get some amount of unburnt fuel, if you will. And it could be potentially at some percent level, even like 0.5%, 1% or so. And by monitoring with a methane or hydrocarbon detector for loss of flame, you can be more prepared for normal operation in case there was type of fuel leak or loss of flame, but also during startup and ignition, so that you light off without having too much fuel in the firebox, and make sure that there's enough purging between cycles, that it's a safe level before light off. So when it comes to safety, safety certainly with a combustible detector, but also monitoring for percent levels of hydrogen and also light hydrocarbons from fuel leaks from loss of flame. So those are really the three critical rules of flue gas analysis. And it really comes down to just the operational set point, the optimization, and the safety. And as I mentioned, there's a lot of trade-offs between optimizing and safety. And it's very much a case-by-case basis, especially if you're going to change a lot of fuels. You might need higher levels of oxygen, but you would also want to monitor for combustible breakthrough and monitor for potential flame out conditions. Okay, so I spent a lot of time talking about flue gas analysis, and it's important to set the stage here because these are going to be recurring themes as we talk about hydrogen. So when we talk about the physical properties of hydrogen, now let's shift gears and talk about hydrogen. If we talk about the physical properties and then the combustion properties, one of the things we'll note is that hydrogen is a much simpler molecule. It's less atoms, also has less molecular weight. So it's much smaller, 8 times less mass compared to methane. It's also lighter because it's lighter weight. It also has less density, so 8 times less. So it's as you know, density rises much quicker if it's lighter, like balloons. In this case, hydrogen can rise much faster comparatively. Average molecular speed, because it's a smaller molecule at the same temperature, at that temperature, it's going to be faster. So if it's in a firebox at 1700 degrees Fahrenheit or 926 degrees Celsius, it'd be 3 times faster, roughly, compared to a methane molecule that's unburnt. And also flammability, it's also much more flammable. If you look at, this is again flammability limits within air, but more flammable. So while the range for methane might be 5 to 15% methane in air, with hydrogen it's up to 75%. It's a much smaller, much easier to break the single chemical bond, covalent bond, and as a result, you're going to get there's much more potential for flammability. So if we just look at the combustion properties by itself, hydrogen is 8 times lighter, 3 times faster, and more flammable compared to methane. Okay, those are some things to think about. Other things to think about are the combustion properties. So if we think about the net heating value in megajoules per meter cubed on a volumetric basis, and a lot of times we see fired equipment sending the fuel at a volumetric basis. But if you're using a volumetric flow meter, you're going to need 3 times the amount of hydrogen in order to be equivalent to the same amount of heat release. So you would need 3 times more hydrogen in order to get the same heat release if you were to use methane. Okay, so now that kind of changes some of the flow measurements. Instead of it being one set point with methane, you're going to need more hydrogen, you're going to need more volume of fuel gas to the burners to make sure they can handle the heat release. So a burner would have to make sure that it could be designed to handle more of that flow. The same heat release, but more flow to the burner, so the nozzle sizes correctly. Now, this is from a volumetric basis. If we look at it from a heating value perspective, from a mass perspective, it's actually just the opposite almost. Hydrogen is almost 3 times more compared to methane for the same flow. So if it's a mass flow rate basis, you need less hydrogen. Most of the time we think about the volumetric side, but it's one thing to think about is that because it's a more dense, it's because it's lighter molecule, more mass can also contribute to more of a heat release compared to methane. So it depends how you're looking at it. So very much important to be mindful of how you measure the flow, mass versus volume. Now, other things to think about is the fundamental burning velocity is also almost 10 times that of of methane. So hydrogen flames are almost 10 times that of methane, which could present an issue of flashback because hydrogen will burn faster. So it'll burn faster. The flames are faster compared to it. Other things is that hydrogen flames are slightly hotter. Again, slightly hotter, not much hotter, but slightly hotter compared to methane. And then also at ignition temperature, because it's a simpler molecule, it's lower ignition temperature for hydrogen, not by much, but still it does exist. So less temperature is needed to react, and also the minimum ignition energy is like 10 times less compared to methane. So much less ignition, much less of a spark is needed to initiate a combustion reaction with hydrogen. So when it comes to it, hydrogen flames are 10 times faster. They burn hotter, and they also have very different heating values to be mindful of if you were to use and switch over to a high hydrogen fuel. Other things to think about is that if you were to, again, try to achieve this same heat release basis, so looking at a volumetric basis, you're going to need 20% less air. Excuse me, 20% less air. So what would have been, in this case, for every 1 molecule of methane, you have 2 molecules of oxygen. In the case for hydrogen, to equate to the same heat release, you're going to actually need 20% less. And this is important to think about because if you're going to switch from hydrogen to natural gas at any point in your process, hydrogen is going to need less air compared to that methane at the same heat release. So as a result, you're going to have to make sure that you gradually increase the combustion air at the burner before you start introducing the natural gas. You don't want to create an unsafe condition. You don't want to create a flame out condition, or you don't want to create even a high combustibles condition because you've not preempted the amount of extra air to the burner in order to handle the methane correctly. So that's something to think about as well. And then finally, NOx. Now there's different cases. I mean, there's different studies, different things that you see, but at the end of the day, there's certainly prop NOx versus chemical NOx versus thermal NOx. When it comes down to just the thermal NOx side of things, it is a shorter flame with a faster flame speed. Because it's a shorter flame, there is a potential risk of higher NOx emissions. The reason for that is because when you have a more compact flame, you have more potential hotspots because it's a small flame. In that small flame, you have the potential risk of breaking down the nitrogen in the air, creating more NOx in those hot spots of the flame. So something to be careful of and be mindful of, especially depending on your permits are written. So when it comes to a high hydrogen fuel, there are some risks to think about that I want to highlight, and it all builds on everything we've talked about so far. So there is the potential risk of flashback. Again, it's faster flame speed, faster fundamental burning velocity that we have to be mindful of. So for any type of premix burner, you should absolutely be concerned about introducing hydrogen and be prepared to have some type of flame arrestor or have some type of precautions in place for a premix burner of any sort if you're going to start to introduce some amount of hydrogen. There's also the risk of, again, thermal NOx increase. Again, hotter flame, smaller flame, potential risk, and also any permits using proper ppm levels versus mass flow can maybe be penalized because you're going to generate more water. So if it's referred to in a dry basis, you may be penalized potentially on a ppm basis for permits. So something to be mindful of, even if it's not a real NOx production, even if it's the same amount of NOx, it may be represented differently when you have more hydrogen, more water in the flue gas and converting it to a dry basis. So something to think about there. Also, the radiant tubes, again, depends on the firebox geometry, but the hotter flame could also have a potential issue. You want to be mindful of that. There's also some risk of overheating metal that may not be expected for the higher temperatures. So again, metal parts close to the flame could also have to be mindful of that. You also have to be mindful of just the metal you're using when it comes to hydrogen, just for the brittleness of it as well. So something to think about as well. The metal that you're using around the hydrogen flame and being careful not to overheat it because of the smaller flame. And then finally, the risk of accumulation of a combustible vapor. Again, there's always this potential risk, but because of any type of flame out or because of any type of high combustible scenario, loss of flame could and should be detected by some type of flue gas measurement downstream, especially as you're trying to build in safety and pull high hydrogen fuel into your system. It is important to also monitor for the accumulation of combustible vapor, and that's one of the risks that I want to highlight specifically when it comes to flue gas analysis, because this is really where flue gas analysis plays a critical role in increasing safety and also reducing risk and being mindful of what is in the firebox. So all of these things are risks to consider, but when it comes down to risk of combustible vapor, especially with the light density of hydrogen being more much faster molecule, much faster flame, it is important to have some visibility on the process itself. And as I said, we've worked with a number of refiners over many decades that have refining fuel gas at 70, even in some cases 80% hydrogen, and being able to watch for, is the fuel completely consumed? Is there any unburnt carbon monoxide, any unburnt hydrogen that we need to be mindful of? Are they in safe levels? So next, I want to take it over to catalytic detectors. I keep talking about flue gas analysis, but let's talk about how can a catalytic detector, how can catalytic flue gas analysis measure hydrogen? What makes it different? So I want to give some time to share this because a catalytic measurement is different than other types of technologies. Now, a catalyst, in our case, we provide two different types of catalytic detectors. We provide a resistance temperature detector, an RTD type detector that is coded specifically to detect combustibles. And we also have a catalytic bead hot wire type detector that is designed to also measure combustibles, with also the opportunity to measure methane and percent levels of hydrogen as well. So those are the two types of catalytic detectors that we offer. And when it comes to what they look like, the RTD type has two different elements. As you can see, you have a active element, you have a reference element. One's coded with platinum. What makes a catalyst? It has a catalyst, the platinum that's on the coating, and how the catalytic element responds versus the reference element is what drives the measurement altogether. But that's just a zoom-in version of the RTD type detector. For the catalytic bead type, imagine two different beads in parallel. I'll show you a picture of just one, but so this is one bead, one catalytic bead. And in the case of the in the case of the active site, the reference would be a little bit different, but there'd be two beads in parallel. One would be the active, so the active, and one would be the reference. If you look at the reference, if you look at the active, you'll see that if there's any type of unburnt compound, and say like the methane detector, for example, any amount of unburnt methane that will burn on top of the catalyst of the catalytic bead, it'll fully oxidize it, and that temperature change versus the temperature change, the current change on this detector versus the reference is what ends up making the measurement. So again, as I mentioned, it's important to recognize that in either of these cases, in either of these technologies, you're going to have an active and a reference measuring element. Now, one other thing to think about is that it will use the available oxygen in the flue gas. So the oxygen is present. That's why we need to make sure there's always an excess of oxygen. But the excess of oxygen exists, and we can use it to measure the amounts of combustibles or amount of methane or light hydrocarbons in the flue gas. So really important. In our case, when there is insufficient oxygen, we actually move to fail safe and go high combustibles, high methane as a fail safe trigger, because we know we need the available oxygen in the flue gas, and we also know that if it's too low of oxygen, there's going to be high combustibles. So that is a fail safe on our side. And it's important to know that because we fully recognize that you need oxygen in the flue gas in order to make the sample measurement work. Now, the next thing to think about is some of the nuances of a catalytic detector. One thing to think about is that these detectors are catalytic. In many cases, they are not speciated to any one particular gas, but rather they're really tuned to a specific zone of reactivity. I like to call it an umbrella measurement because it's not just carbon monoxide, it's not just hydrogen, it's not just methane, it's actually the umbrella in which they react. And so it's for combustible measurement, the umbrella is really between carbon monoxide and hydrogen. Any amount of ketones that could be part of the subreaction, they could be detected as well. But a combustible measurement cannot measure methane. It just doesn't operate hot enough. So it's important to think about because calibration really plays a role in refining the measurement and also defining. It plays a role in also defining that zone of reactivity. Now, that being the case, as I mentioned, like the hot wire type detector can be used. It operates hot enough, hot enough currents to crack methane, and it also can operate hot enough to handle high sulfur applications, which is why we have two different types of detectors for these combustibles and for methane. But just something to remember is that they are both capable. Again, they're both capable of ppm level measurements. The catalytic hot wire detector, the catalytic V type, is capable of percent level measurements. And when it comes to using these catalytic detectors in high hydrogen fuels, you absolutely have to calibrate with some amount of hydrogen. And so I want to emphasize this because catalytic detectors really tune it to the range. And if you want a good sensitive reading for hydrogen, we absolutely recommend calibrating with hydrogen in some amount in the calibration gases. So when it comes to combustion measurements, building off of what I mentioned before, when it comes to high hydrogen fuels, you're still going to need some amount of excess oxygen for safe combustion control. You're going to need to make sure you have an excess of oxygen in the flue gas. You have that process operational set point. When it comes to combustibles, having the visibility for the ppm level monitoring for hydrogen and for carbon monoxide, monitoring for that combustible breakthrough point, also having optimization, that correlation between the air to fuel ratio, visibility on that as you can optimize it. When it comes to hydrocarbons, hydrogen and light hydrocarbons like methane, having the ability to detect a fuel leak, loss of flame, also safe light off during startup. You want to make sure that the fire equipment is purged correctly before you light off again. So that's for high hydrogen fuels. When it comes to pure hydrogen, very same case. When it comes to combustibles, though, you're really going to be monitoring for low levels of hydrogen, ppm levels of monitoring for hydrogen. Certainly, you want to prioritize the oxygen measurement, make sure you have an excess of oxygen for high hydrogen fuel, but also monitoring for that amount of incomplete combustion for hydrogen. That's going to exist regardless of because of the nature of poor and incomplete combustion and poor mixing and variable fuels and such. Finally, but it really comes down to also leveraging the methane hydrocarbon detector that we have also as one option for monitoring at percent levels of hydrogen for safety. So for monitoring for burner leaks, for fuel leaks to the burner, for safe light off, and so on. In many cases, a lot of people are talking about lighting off with natural gas and then moving to hydrogen during normal operation. Being able to switch from methane to hydrogen using a catalytic detector, there's no issue for that. You can calibrate the analyzer one way with hydrogen, some amount of hydrogen, or a mix of hydrogen and methane, and you'll be able to detect that regardless of whether you're starting off with natural gas or some other fuel. So important to think about there. Even with hydrocarbon detector, you can still measure hydrogen in a catalytic way. So some takeaways. I know we're getting close to time. I'll answer the question in just a moment. So just some takeaways. So really when it comes down to hydrogen fuels, again, that really, when it comes to decarbonization and reducing CO2 emissions in the existing combustion processes and existing refineries and existing heaters and chemical plants and so on, it really comes down to providing the most versatility for small dispersed point sources. Um, like we mentioned also before, flue gas analysis plays the important roles of operational set point for the air-fuel ratio, optimization, and safety. Those are really important elements when it comes to any type of flue gas analyzer. Hydrogen, from the physical side of things, is 8 times lighter. It's faster diffusing. It's more flammable compared to methane. For hydrogen flames, 10 times faster, burn hotter, different heating values. So you got to be mindful of those. And then really when it comes down to hydrogen fuels, again, that potential risk of flashback, being mindful of making sure that you have enough oxygen when you switch from methane to natural gas, or from natural gas to hydrogen fuel, from making sure you have enough oxygen available when switching from hydrogen to natural gas, and also be mindful of NOx emissions, especially in your particular case and how any of the permits may be written. And then finally, like I mentioned, catalytic flue gas detectors, catalytic flue gas analysis leverages catalytic detectors. So making sure that these catalytic detectors are tuned appropriately for hydrogen, calibrated appropriately so that you have the right umbrella reading, with the right being able to measure for combustibles at ppm levels and percent levels of hydrogen and hydrocarbons for safety. So with that, I see there's one question in the chat, and I welcome any other questions that you may have. One thing that I see, the question in the chat is it the same detector to measure ppm levels of hydrogen and percent levels of hydrogen? The short answer is no. It's actually 2 different detectors. The combustible detector is capable of measuring ppm level measurements of carbon monoxide and ppm level measurements of hydrogen as one single combustibles measurement. The methane detector that we offer is capable of measuring hydrogen and light hydrocarbons. And the reason why I say that at percent levels, and the reason why that's important is because it operates hot enough to crack methane. It's also designed sufficiently to handle that percent levels of detection. So it technically would be 2 different detectors, one for ppm level measurements and one for percent level measurements. Good question. Any other questions? Okay. Well, I appreciate your time today. I'll stay on if there's any other questions. But that being said, thank you for your time today. Again, my name is Tim Talon. I'm Combustion Product Manager here at AMETEK Process Instruments. Feel free to reach out to me or any of my colleagues if you have any specific questions. But I really thank you for your time. And have a great rest of your day.